You might not be in the big FANG, the big tech companies, but there's lots of jobs around America, especially if you're willing to move. If you're trying to stay in Ann Arbor, it's actually not that bad. You'll probably work in the automotive sector. All right, so let's get started. Let's see announcements. Homework 2 is due today. Homework 3 will be posted. When will it be posted? Posted this afternoon, probably tonight. Office hours right after class today to help with homework. Reminder that for Lab 2, in-labs and post-labs are due the night before the next week's lab, so you get a full week to do them. And this week you'll be starting Lab 3. And the pre-labs are due before you go to lab. Any logistics questions? All right. In embedded systems, we often, like I said before, it's a wide range of topics you're responsible for knowing. And one of them that always comes up is what's a voltage regulator, or how do I connect my battery to my board? So your ESP or STM32 requires usually 3.3 volts. Some of the dev kits can take 5 volts, but the IC actually runs at 3.3. But your battery voltages range from, for lithium ion, will start at like 4.2. They say 3.7, and then they'll drop down to 3.2. So they actually change their voltage over time, and you need some device to control that voltage so that it always puts out 3.3 volts, and this thing is called a voltage regulator. You don't have to know how they work, other than that they do work. And the trick is you can get really simple ones. They just have 3 pins, and you just look at the specs. You can usually put in like anything up to 12 volts, and your desired voltage will come out if you buy the right one. They're really easy to use. They're just not power efficient. And then there's things called boost converters or buck converters. They're switching. They're much more efficient, but they usually take up more space and are more complicated. So when it comes to actually making your little prototypes, especially for your projects, you will probably need, if you're battery powered, you're probably going to need some sort of voltage regulator. That's what they do. Yeah.
Basically,
No, they actually control the output voltage.
Oh, okay.
Let's see here. Let me see. I can run. Oh, you can't see that. I can see it though. Hold on. I'm gonna go here, there. You guys can't see it very well because computers are hard. Don't worry how this works. This is too confusing, scary, and it may involve analog circuits. We don't want any of that. We just say we have a variable voltage source, which we are going to measure here. So that's that green line going up and down. And then this is your output should be, let's see, output should be here. Stable output is 12 volts. So no matter how I change the input voltage, and you can see it wiggling up and down, the output voltage here stays constant. And then this is even pulling different amounts of current. So the job of this thing is to kind of always control the amount of voltage so that the system, no matter how much load it pulls or how much the input voltage varies. So what would be an equivalent thing? So you got a hose and you have to put some amount of waters per minute on a fire or something. And so you're constantly, and it's got to hit a certain range. So you're constantly modifying how much pressure goes in and out of the hose to hit your target. Did that answer people's questions? Any other questions? Okay. But you can go back to this thing here. Yes?
So is it dependent on each voltage regulator what voltage is in, like, the wire? I'm assuming it's in the wire.
So this is your output?
Yeah, like 12.12 is.
So you'll have, so you'll go online, and they'll have a product family. So say it's this one, and they'll have like 12 different ones, and they'll have different output voltages that they're tuned for. Some of them, especially ones like this one, you can put a resistor in there, and you can like hardware define it. So you put a feedback resistor in there, usually in a certain ratio. It tells you in the data sheet, and then it will try to regulate to that equivalent voltage. So it's like you define the output voltage by a resistor. What do you think?
Yeah.
You think that is possible? Okay, it is possible. Yes?
Can you make the voltage higher at all with these or no?
There is a circuit called a boost converter, and it's a switching circuit, and it can boost the voltage up. Of course, you're going to sacrifice current. They are a little bit painful to use. I would not recommend any 373 students to use them just because they're painful. So we just get you more batteries so that you're always dropping down.
Okay.
What it does is, because boost converters and buck converters, these switching converters, they have weird startup conditions. And sometimes they can go in odd states. They're not as robust as the linear regulators, which are the more simpler devices. But their boost converters, buck converters are highly efficient, so you can be up in the 90s. While these guys can be like 10% efficient, depending on your division ratio, maybe 50%. So there's this trade-off. But usually for your 373 demos, you are trying to make it last for 3 hours. So, all right. But if you have more questions, come to office hours. You can play with this Falstad stuff, or just go look on Falstad in general. They have other regulators that you can play with. All right. So today we're going to switch to this concept of memory mapped I/O. So this is kind of where we step out of the things that were taught in 373 or 370, I mean, and start talking about new material. We're going to talk about the concept of memory mapped I/O, bus architectures, and then the specific bus on the STM32, or at least the ARM Cortex M4s, which is the Advanced Peripheral Bus that allows the core to talk to the peripherals. So I remember our diagram, mostly we've been in here. Now I'm talking about what's the actual like nuts and bolts signal mechanism that allows us to talk to these other things, especially the GPIO, which we call memory mapped I/O. I mean, all these things are memory mapped I/O, but the I/O input output is really comes from the GPIO, where a lot of this stuff started. So remember, we had the Cortex M series has been defined memory allocation. So ARM defines this memory allocation. Now, I had some questions before, because remember I said that like sometimes they've added, I don't know what this is, half a gig? And you certainly don't have a half a gig dedicated for code space. And so imagine it's kind of like the city plans out a development. And they said, here's all the addresses to all the potential houses. The developer says, well, I don't want to put a house in every plot of land. I want larger plots of land, or I don't want to just leave some unused. And they can put a house just in a few spots on that city's plan. That's kind of equivalent to this, where ARM says, hey, here's all the addresses and all the space that you could put things. And then STM or NXP or some manufacturer will say, well, I only need this much code space. I need this much SRAM. I need this much for peripherals, blah, 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 blah. So that's why there's that holes in the map that I showed you kind of on day one. Does anybody have any questions about that? Remember, if you ask me questions, I will teach you things. That's literally my job. Fantastic.
External device, what if you like plugged in something that has like more memory than
allocated? You won't be able to address it. I mean, I suppose there's workarounds, but not using the mechanisms that we have, which is loads and stores purely. Yes?
So like if I had like a 2 gigabyte SD card, I wouldn't be able to access like a whole gigabyte of it?
We're actually going to go through that example, but not without having some other mechanisms that's beyond the core, the loads and stores the core provides. We could add another information layer on top of it. We'll get to that. Okay. So here, in an example, we have that code memory space. And the idea here is this is all distributed throughout your chip. Now, of course, the core doesn't know that. The core assumes it's just, hey, stop that. Okay, the core doesn't know. The core just looks at this as unified memory. A load to this address is the same as a load to this one. Store is all the same. It doesn't know that when you're talking to something, it might be the peripheral or the external memory. But that's part of the simplicity of the architecture. ARM doesn't have to keep track of it for everyone. And it just happens to be that, say, the external RAM here is accessible through a bunch of addresses, and that happens to be hanging off of the high-performance bus. And peripherals are typically hanging off of the low-performance bus, although some are here, and then the external devices are on the peripheral bus. And then SRAM and flash are typically in off of the high-performance bus and the data path and instruction path. And then so if we keep going, like in lab, you've been talking to GPIO, and they have certain addresses. And so what ARM's done is just said, okay, well, ARM and STM together have just said, hey, here's the allocation space for GPIO A, B, C, D. So those are different ports that you would have. And then in just one of those addresses may be something like your output register. And all that is just a memory address. So it would have some memory address that would go here, and you could put bits into that address. And that is just a series of D flip-flops. Right? So that's like the state holding mechanism. We're not talking about SRAM as a different state holding device. It's usually in the peripherals, it's just a bunch of D flip-flops that now the peripheral itself can reuse to do tasks, or sorry, can take this information and then have some output. So that's kind of like homework problem 1.2, where we're saying here's some D flip-flops. Essentially, let's say we don't have any addressing architecture. We're just going to put data into it. And then this peripheral is tasked to do something, right? It's supposed to turn on the green LED, turn on the red LED, turn on blue LED. You do that when some data is put here. And then your job is to make the combinational logic to turn on those lights over there. This is just the peripheral, like say, output register of the GPIO pins. And you just have a special GPIO pin that does these things. Okay. Yeah.
A question. In the previous diagram, you showed that peripherals are from both the high performance and the advanced performance. How does the decision to which, I guess, peripheral bus is used, just like specific?
Well, there's different goals here. So like GPIO is on the advanced high performance bus. We used to use, I forgot the name. We used to use a different microcontroller in the past, and that company decided to put the GPIOs on the advanced peripheral bus instead. So the manufacturer, so in this case it would be STM, has decided where the peripherals should go, and that's really where their special sauce is in the marketplace. They're saying, I'm going to make slightly different peripherals than my competitors. Maybe they have really good ADCs or a camera module. In this case, STM said, I want to have really fast interaction so my GPIO pins can go really, really fast. So that's why they've put it on the advanced peripheral, or the high performance peripheral bus. Or I guess it's not it's just the advanced high performance bus. Does that answer your question?
Yeah.
Okay, anyone else? Okay. All right, so the basic idea of memory mapped I/O, we'll start with a counter example. So there's a thing called port mapped I/O, where the CPU uses special instructions to do a task. And this is more like in RISC, not RISC, but like x86 architecture, where you have a bus that's just for memory. You have a bus that's just for video. And so those have specific instructions, and those instructions only do the tasks, say, of uploading your video or updating your video card. That's great for specialization, but that's not where we're at. We're at the microcontroller level, where we're trying to make an architecture that works for everyone. And so memory mapped I/O is simpler and a more convenient way to work with I/O devices, because you don't have to know the special instruction. So each device is just, from the core's point of view, or each peripheral is just a memory address, and the CPU is just going to use loads and stores to access all those different functionalities. If you're going to talk to the external memory, internal memory, or external memory, external devices, the peripherals, it's just loads and stores. So it's lower performance than port mapped I/O, but it's easier to construct because you don't have special instructions. And so here's an example. Here you're going to do you have your core, you do some store into some address, and say this address represents, the data in here represents a GPIO pin, and now you can have this, by using a store function, you can make a GPIO pin go high or low. Yeah?
So there's a difference between memory mapped I/O and port mapped I/O. Line left internal the chip versus trying to the chip.
I think both go from their perspective of everything's external to the core. So you could have port map instructions to do special tasks on a device. But memory mapped I/O is the only way, and is a good way, to go talk to the external world as well, off chip. Does that make sense?
Special instruction then, because is it an assembly instruction?
No, it could be like update video. I don't know. It's been a long time since I ever looked at x86, but they have special instructions just for sending things to memory. That's not load or store, right? It may be, hey, I want to take this transfer file from here to here, or I want to update my my video card, right? They have a whole port just for video. And so now you have instructions that aren't load and stores for video. It's like make a polygon here or something. Yeah.
Why?
Real loud.
Why is memory mapped I/O lower performance than port mapped I/O?
Because port mapped I/O can be specialized. It does one very important instruction, so you could probably get multiple things done with one instruction. While memory mapped I/O is just, I'm just going to put data at these addresses. So you get to optimize better for memory or port mapped, but it's not as flexible, or it's more complicated. Yeah.
Loads and stores, you're using memory map, you're using some specialized non-loader store, then you're using some port map, basically.
That's true, but this architecture doesn't have port mapped. This architecture only has loads and stores, so it's just a different chip altogether. Yeah.
So everything we've been doing so far is memory map, right?
Correct. I mean, I guess a move, just to bring it back, like a move instruction is not memory mapped I/O, because it's not using a load and stores. That's just how can move information around the internal of the core, just the registers in here. Yeah.
So memory map I/O is writing a values to memory, but then the port map is, say like we connect the register to the port and we write a value into the register, which gets like transferred to the port.
Yeah, you can look at it that way. I mean, that could be a way to implement it. I'm not saying that's how it's always done. Yeah.
So why is it called port maps? Like, what's the port?
Because you have instructions that go to a port, like an X out, you have a GPIO port, which is a group of GPIO pins. You could have your video bus on in your application class processor, and that video bus can't do things like turn on LEDs and all that other stuff. It's designed for one particular task, and now I have instructions to do one particular task. So they're not inflexible instructions. They're good questions. All right, so we'll move on for a second. So here we're talking about external memory devices, and I have a 1 GB card. It happens to be 1 GB. So how do I interface with this thing? And I want you to kind of think through this and talk with your neighbors. Now the goal is you have to use loads and stores, but you want to minimize on-chip memory, right? You don't want to have a gigabyte's worth of data here to be able to talk to a gigabyte's worth of data here. Then I don't even need this anymore, right? So, and it would make the cost of the chip very high. So how can I manipulate this peripheral such that, or construct this peripheral such that I can use loads and stores and I minimize how much on-chip memory I have? So why don't you take 30 seconds or a minute or so, talk with your neighbor, come up with a possibility.
Maybe something like indexing to like into it.
That's like at a little bit iPad, and now I feel like a bot because I like don't know.
Go with the range of addresses. And now I get
Oh boy.
I know.
Yeah, vacuum cleaner.
Well, I said like.
you don't have like they can say you had a
Why it's so buggy? It's like the lights are flashing, but the screen is black. And I was like, maybe that'll fix it. Or I look like how to code.
I wouldn't make reading software complicated.
All right, just to make the problem more explicit, what you don't want to have to do is have a gigabyte's worth of registers here, or memory locations, or SRAM or whatever, just so that you transfer the same data one-to-one mapping over here. That would just be a waste. So what else could we do? What would be a more size-efficient mechanism? Or what? Yeah. Yep.
Okay, so it's like, kind of think of how cache works. You can have like a small chunk, and then you can map it to a specific section of the external register. And when you want to like change the part of the SD card that you want to access, you can change which part of it you want to map to.
Yeah. So that basically works. That's basically a version of what they do. I would say they just have a state machine in here. It takes in an address, right? So the state machine is looking for a range, anything, it will respond to anything that's within the range of addresses. I forgot what it was. And then when it says go to this register, this address offset something, then it says, oh, well, that just means somewhere in this card. And then it's just going to take the data and just transfer it over to the card. Now, this peripheral will actually talk this particular mechanism, but from the core's point of view, it's just it's just memory addresses, and then there's just some state machine that's negotiating the transfer back and forth, right? So there don't actually exist all those registers, or all those memory locations. It's just not useful. Yeah.
Like a virtual memory?
I wouldn't call it virtual memory. No, just think of it as a combinational state machine. The cache analogy is fairly reasonable. It's just something that takes in addresses and says, oh, you're in this location. That means I go and store data over here. Yeah.
Isn't that like kind of like a waste? Because you have like 1 gigabyte of storage on your memory
Right.
and 1 gigabyte in your.
But you don't. That's what I'm trying to say. We don't have this.
Right.
That would be bad. We just have a state machine that is literally combinational logic.
Okay.
Right?
Oh, so you have that gigabyte of addresses. So
Yeah.
you can address into all of them.
Right. So it's looking for. It just says, okay, if I get any memory loads or stores that are from A, blah, 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 up to E, I'm just going to take that data, and I'm not going to store it here permanently. I'm just going to then move it over to there. Yeah.
So when it reads data from the SD card, where does it store it, or does it have to fetch the data every single
It's got to fetch the data, and then it has a small bit of cache, essentially, in here, let's say, but has a small bit of register space in which it pulls it in. Now, this is not supposed to be fancy like a full processor. It may only have 1 or 2 registers just to store this data, and it may have a page's worth or something of registers. But it's not going to act like cache. Well, not at this stage where it's trying to always have the most recent data. We're not trying to be that sophisticated because we're in the 100 megahertz range, right? That's our clock speed of our devices. We're not trying to get the most out of every cycle. If we wanted that, we just move up to another processor class. Yeah.
So like, if I had like a much larger SD card, like
64 gigs, yeah.
64, 256, whatever it might be, and I had like large files, like just individual pictures.
Yep.
How would like plugging a new SD card? How would that work with plugging like a new SD card into a device that hasn't seen it before? Like, would the state machine automatically be able to associate and like parse the data back in so you get your images like together? I don't know if that's a confusing question.
Those are great questions. Beyond the scope of this toy example, and what you would do is then you'd read through the SD manuals and you look up the external device peripheral and see what it says. So I don't know about hot swapping. I know it does have some provisions to go over a gigabyte, but then you have to store into certain registers that say I'm in this upper range, right? You're setting an offset with that register. So there's these extra functionalities. It's just beyond this toy example.
Okay.
Yep.
How do we manage that memory that's going onto the SD card?
How do you manage it? What's that mean?
Yeah, because it seems like we have arbitrary accesses from like A to E, and then we just push it onto the SD card.
Yeah.
We manage like what's like.
You, the programmer, has got to manage it.
We have to manage all the external data on the SD card.
Yeah. We're bare metal programming. You are here fighting bits, and it's your job to keep track of it. Now, there is a thing called an RTOS. You can get a real-time operating system for this. Nobody in this class needs to worry about that. You go to 473, they'll teach you about RTOS. Okay. Guess I said all that. Okay. So what's memory mapped I/O? It's a method for interfacing with peripherals and other elements. They're essentially outside the core. And then, just to be clear, peripherals can be external devices as well. Like we're going to talk about memory or storage as well. And the key idea here is, from the core's point of view, is just loads and stores. That's the only instructions we need to interact with them. Yeah. Okay. So let's move on to the bus architectures, which is the mechanism for which the core is going to talk with these memory mapped IO registers up there. So a data bus is just a set of wires along with protocols and circuits. It allows you to transfer data between two locations. If it was just really just two locations, it would be super simple. But the trick is it's not. And then there's two general types of buses that we'll learn in the class. There's parallel buses, and then there's serial buses. So parallel buses transfer all the data, all the bits of the data simultaneously, while serial interfaces does it sequentially. Why would you choose one or the other on chip? Does anybody have an idea?
Much faster data transfer.
Yep. So why don't we just use, so what do we use? Should be that on-chip connections or off-chip connections?
Off or on-chip connections.
What? Yeah. Why not off-chip connections? Why don't we use this for getting data off of chips? Yeah.
Because we don't have infinite number of pins on each chip.
Yeah. So here, I'll give you an example here. So this is an 88 microprocessor from Intel, one of the first ones. These are the pins that they have. It's much harder to get data on and off chips. This is why the bottom of like a CPU has all those little bumps on the bottom, right? It's trying to get as much data off and on. And actually, you're really defined by how many pins. I didn't believe it when I first took these sort of classes that it was actually limited by pins. And then it's thermals as well about how much data you get off and on. So if you have this device, we have all these different functionalities. We have ALU and registers and instruction registers and decode registers and some stack pointers, and they're all distributed throughout the chip. And if you look, they all need to share data in some way. So this is the bus structure that links this chip together. And here it's an 8-bit chip those are the rainbow colors. So like that's these, and this is power, this is ground. And so the idea is if it was just two modules that are just next to each other, go back here, well then sure, you could, and they are literally connected, but it's when you want to share the data to any one of those devices is when you need a bus. And then just to make it clear, I put a Fallstat example in here. You guys can just go through the slides and you just copy this link and you can go put it in your browser, you can play with it. I'll show you what it is quick, but if you have any questions, this is a way to reconfirm your learning. So here, this is a digital counter here, and it's just counting up. We can see binaries going up, and it's been going on for a little while. So we're just counting up. And then every clock cycle, data is held in these D flip-flops, so there's 8 of them. And then when the clock cycle is transferred over here, it's latched in, and then it goes to this display module, just sync binary to DEC. And so this is just the most simplest bus structure you could possibly have, where data is being transferred over on every clock cycle. But we haven't talked about any addresses in here or anything else. So there's lots more that you need to be able to get data passed through rather than just wires. So why don't you work together and think through what are the other signals, other things you need to keep track of when you're trying to send data from the core all over the chip. You take 30 seconds or so, work together, see what you come up with.
I don't think that's very
Yeah, but that's definitely true though. You have to keep track of how to do it.
Yeah, I'd be on data, maybe like data.
We're just like about
That's all I got.
Stop. I did that 2 seconds.
All right, what do we think? What else? What other signals would you need other than just your data in your clock if you're trying to distribute data or send data all over this chip?
Yeah.
Yeah?
Where it's going.
Right, so we need some way to control, we have some address lines, right? So address lines tell a different peripheral, hey, This thing, I'm talking to you, or I'm talking to you, or I'm talking to you. All those things have to have an address, and you need lines, data lines, or control lines to send that address bit over so that people know, or the devices know it's being talked to. What else could you need?
I have a question. Is this coming off the board, or is it still parallel bus?
It's a parallel bus. There's a state machine just off the port called, well, we'll talk through it. It's called a bridge, and it will take your loads and stores, turn them into bits that are sent across the bus. Yeah.
Like type classifiers, like type of data?
Type of data. Does a load or store keep track of the type of data in any way? No.
Reset?
Reset, right? Sometimes your bus might screw up. You need to have a reset. What else could we use?
Hold in case, you know, this particular data.
Yeah, so you need a hold or some sort of way to say, well, wait a second, I'm not ready for more data, or I am ready for data. Okay? Any other control lines you can think of? Yeah? Either, take it to, yeah.
Acknowledgement so that like the write or read is complete.
Right, that's a great one.
Some sort of data validation to like something got screwed up along.
Ooh, like a CRC bit or something like that. Yeah, we typically don't, that's a great idea. We look at those for device to device, so off chip, but typically there's no CRC or dirty bits or any, not dirty bits, what do you call it? I forget. But there's no, usually don't have that on device because the signal integrity should be pretty good. So here's what I came up with. So ARM has the terms, requester and completer. That's what their terminology is like the, these are the peripherals over here, and this is the bus controller. And so you have data lines, M of them. You have some address lines. You have a clock. There's usually a bunch of control lines. And so I think we've hit all the classes here. And then the idea here is that this receiver, this completer, is going to respond to different addresses than this one is. And then the data lines go to everything, and the clock line goes to everything. And then there's different control lines to work with flow control back and forth. Yep. All right, so terminology, we just talked a little bit about it. ARM calls these high performance buses and the peripheral bus. You have the requester and the completer. So in this world, the requester is the thing that controls all the bus traffic, and it initiates all the commands. The completer or the peripherals cannot request to have a conversation. It's always driven by the bus controller or the requester, and that's just an architectural choice. You could make a bus architecture where everybody can ask and demand to talk. They get more complicated, so given the class of this chip, it's very common just to have one thing that's in control. We're not using the bus. The completer must not transmit to avoid short circuits or bus contention. You don't want to have two things talking at once. And there's actually an explicit method for that. And they use these tri-state drivers to disconnect from the bus altogether. Another thing to remember, we'll look through a diagram in a second, is that some wires are shared with all devices while other ones make point-to-point connections. So just to bring this home, we have the core. The core, somebody basically asked it, how does the core talk to a peripheral? Well, there's this thing in between, right? So built into the core, essentially, is a state machine, this requester. And this instruction gets executed, and that part of that instruction, somebody's looking at the, the decode bit and saying, okay, it's an instruction now. And it's the requester's job to actually get the data out of, what would it be, R7, right? And then and that becomes the address, and then you have the actual data in R1, which goes onto the data line, and that is stored somewhere over here. And this state machine is going to figure out, oh, okay, you wanted to talk to that GPIO pin out over there. Okay. Yep.
But there's not. You said so. There's not too many pins on the chip.
This is all on chip.
The peripheral's on the chip.
The peripheral's on chip. Yes. That's fine. It's just a terminology problem, right? ARM tried to mess you up today. You can have external peripherals like what would we call that? I'm sure there's a device that, like memory sometimes on some embedded systems would be called a peripheral. But here, in the context of this class, a peripheral is, let's come back, this is an entire diagram of everything that's on your microcontroller. And this is, these are all considered peripherals. Some of these peripherals will talk to the external world, but a timer doesn't necessarily. It just keeps track of time, so it doesn't actually going to be connected to GPIO pins. I forgot where it was. Here we go. What questions? Where did I go? Yeah. So yeah, we're trying to figure out what's the data range. Is it a load or store? Trying to keep track of the target address. Is generating its own clock. It has to generate the control lines to talk to one of many completers. And then the completer's trying to figure out, okay, based on these control lines, am I going to receive data or is my job to push data up? It's trying to say, in trying to do control to make sure, like maybe you're going to talk to a peripheral that takes a really long time to go. So it has to have a line that says, okay, I'm ready to send you data or I'm ready to receive data. There's no guarantee for the low performance bus, or what do we call it, the peripheral bus, that things will be completed within one clock cycle. All right, any last questions? Yep, let's go back over there, yeah.
Can you explain what a control line is and what it exactly does?
Sure. So we'll go through more detail. These are the cartoon versions, and we'll get to the nuts and bolts from the manual version. But a control line just says is ways in which we want to negotiate the conversation between these two. So basically, one's just like raising your hand, right? So it says, I'm trying to talk to you now. It's your job to pay attention. That frees the completer from having to look at every single address and doing, basically computing, is the controller talking to me? It also, control lines could say like, hey, I'm not ready for data, or I am ready for more data, or when it's sending data back, hey, my data is ready to go. So these are bidirectional, or can be bidirectional data lines. Yeah?
So if we sort of like kind of step by step, is the requester sort of like, is there for decoding what's coming from the core?
Yeah.
So like a two-stage decoding of the completer as well? Is it fully decoded and we know what everything is doing by the time we get to the completer?
I think by decoding you mean, has it figured out what that is? So these two are basically designed in tandem. They work right next to each other. This thing, at this point, has figured out completely what this instruction does, and has translated it from this binary instruction to turn it into the action of actual data that was in, what would it be, in R1. The address that was in R7 generated its own clock and now is controlling it. So it's not that this thing has to decode this instruction. This thing has to respond to these lines that have been generated.
So it'd be accurate to say the requester is going to understand what the core is talking about and put it in a way that the completer can work with.
Correct.
And then interact with the peripheral.
Right, and the whole goal is what we're not showing here is there are hundreds of these completers on your device, all trying to complete tasks defined by the requester. And they're trying to share as many of these lines as possible so that you just don't have an explosion of wires on chip. So let's go through a little bit more examples, and we'll get to some concrete examples that might answer some of these questions as well. So on your device, this is just informational. There's the Advanced High-Performance Bus. This is really good for high-speed data transactions. It's particularly interesting. It's actually a pipeline bus structure, just like a pipeline processor. This is like a two-stage pipeline rather than like you looked at like three-stage processors in, or actually this Cortex-M is three-stage. But this allows more data to go through. It has good for burst. It can have multiple masters or controllers. I should update that to the new terminologies. And then it can split transactions up. Now, the Advanced Peripheral Bus is lower power. It's simpler interface. It can be blocking. This thing is designed, this bus right here, is designed to be slow. So doing things like SPI, which is talking to devices off chip, is a protocol for external communication, it might have to wait a long time for data to come back. So it's much more, this bus is much more tolerant to latency than the other bus. And then for the purposes of this class, so, there's also like this, bus matrix is also another term for the advanced high performance bus. When we talk about DMA, so there's direct memory access, this little controller actually acts like a mini core in some ways, and where it can route data directly from like GPIO to memory without having to go through the core. We'll talk about this, it'll be like one of the last lectures in the class. But for now, we're just going to assume, we're just going to look at the advanced peripheral bridge. So how the advanced peripheral bridge talks to the peripherals. I could try and teach you how the advanced high performance bus and the core work, and then it would be too much and your brains would explode. You'd all revolt, nobody wants that. We're just going to assume that the advanced peripheral bus and how it interacts is functionally equivalent to how the high performance bus works, and it is, except for the pipeline. So if you know one, you're going to know the other one. All right, so where can you get more information if you need to? There's a manual that's actually not 1,000 pages long. I think it's only like 100 pages long, and it defines the spec for the advanced peripheral bus. So if you needed to, you can go look through that. I'll be drawing my examples from that. We'll look at some notation as we go through the rest of the diagram. So you have like clock. This is just showing you what the transition from high to low symbol looks like. This is just showing you there's some uncertainty in that signal. Same as high to low. This is the bus is stable but undefined. This is the bus is in high impedance mode. That won't come up very often. This is just the bus was changing. And this could also mean that there's multiple bits of data on there. A symbol like this could be 32 bits. We'll show that later. And this is a bus going from high impedance to stable condition. We won't care about that so much. So look through each one of these signals. These are the signals between the requester and the completer. So we have, what was this? Ooh, fancy. You got P clock. So this is just a clock that defines the system. We have the address. So this is the address. So this is going to be multiple bits. Now, in class, we're just going to say that's 32 bits. In reality, you don't have 32 bits worth of peripherals. So the requester takes that address that's given and may truncate it because it can represent the same values within a smaller area. In fact, we don't exactly know what STM has done when we had, it was the Actel. We had Actel boards before, which had an integrated FPGA, and we knew exactly what was going on. But for this class, we're going to just say that it's 32 bits. Then there's a P-write signal. So these are all wires, right? And the P-write is going to define, the requester is going to define whether it's writing or reading. So 1 for write, 0 for read. So in this is an example, this would be a writing action. Basically, you're storing something. Okay? We have P-write data. So there's a bus specifically for writing data. This will be 32 bits wide. And here we're just showing that it was something, it transitioned, now it's some other data, it's going to transition again, go back to some other data. That's what those symbols mean. P-select, so a peripheral, there's dedicated lines to select individual peripherals. That's different than registers inside a peripheral. That helps just, so all peripherals don't have to decode all bits, all addresses all the time. So there's a specific line to tell a peripheral to turn on. Now, a peripheral could have multiple addresses inside of it. So it's not just the same as the address line. It's actually a dedicated function, and there's multiple peripheral selects. We'll see that later. We have peripheral p-enable. Yeah, so p-enable, what is p-enable? Oh, p-enable tells that the peripheral that the data is ready. And p-data, p-ready, is the target, we should have said responder, that says, now I'm ready to do the action. Whatever it is, I am ready. So it could be ready in one cycle, or it could take multiple cycles to become ready. What questions do we have so far? Yeah.
What does this device mean in P-select?
You gotta say that loud, I'm old.
What does this device mean in P-select?
P-select. Oh, this device, like this, let's say that this, right here, this table is a peripheral, and this table is a peripheral, this table is peripheral. The P-select is saying, I'm gonna enable this peripheral. Now, each one of these students has an address inside that peripheral. So all it's saying here is, we're selecting a particular peripheral, not all or not any individual student. That's probably bad nomenclature.
Wait, is there anything that to select each different computer? Or is that the same thing?
P-select is each completer.
Oh.
Yep, so each row here could be a peripheral for a completer, yeah.
So if we think of this as picking like a specific port, like port A to enable.
Yeah, that's what a select would do. And then inside a port, you have like, not only do you have the output register, you have the input register. You also have the control register. Those are all different addresses on a port. Yeah.
So P-ready is the only thing that the requester sends back?
Correct. Other than data. We'll get to its data in a second, but yes. Yeah.
So it's like so you use the word asserted in there. So is it just, it's just like a verification that, because you normally do like isn't all these things addressed by like address inside like where the read or write is going to? So like, is the P-select just like a check on that, or like?
P-select is a way to, let's just advance a little bit and I'll explain that answer. Next diagram should help out, or next couple diagrams should help out. Let's see. All right, so let me just go through this diagram. We'll get back to your question a little bit. So what's happening here? Okay, so first we have a clock that's going through. We had a P-write. So P-write is high, meaning this is a store. Some address has been asserted here. That T, between T0 and T1, normally in these diagrams, they're showing you with the previous state in. The action is starting here. So an address has been asserted. It's been defined that it's a write. The peripheral has been selected. Now that this data, you need a clock cycle for the data to stabilize. Right? So yes, it shows it up here that it's stable, but it needs a full clock cycle. And then it says, okay, P-enable. Basically, the requester is saying, hey, I have established all the data required for this transaction here. It's your job to do a thing. And actually, the data was also established here. So it says, all this data is ready, now do your thing. And then the peripheral in this thing says, hey, it didn't matter if it was high or low before. It didn't matter because it wasn't even talking to it. Now it says, okay, now it's your turn to respond. Are you, tell me when you're done, and it says, I'm immediately done. Just happens to be for this case, it was done immediately. And that's a typical case when you're just talking to a flip-flop. And then it comes back and it says, okay, it releases, I'm done, or no, this thing deasserts that peripheral and says, well, it doesn't matter what, it can either be high or low. Okay. Yeah.
How is the P-ready like immediately ready? It's just like...
We'll go through examples where if all the data is here, all the data is available, and you clocked it in on the next clock cycle, those D-flaps would have captured it. D-flaps have just captured it in. Now you're immediately available. Immediately did that task. There are things called wait states where it may take multiple clock cycles for peripheral to complete, and that would be deasserted low. Okay. I'm not being very clear here. What else you got?
So just to make sure I understand, so at T2, that's when the peripheral sees that the controller wants to write to it, and it does the writing within that cycle. And then at T3, that's when the controller sees, okay, the peripheral is done now?
Yep. Okay. Yep. Okay. Let's keep going through some examples. I still have a whole question I got to get back to. Yep. When's it latched in? All right. So here's the written example here. That you guys can go through later. Let's go through the architecture, which will answer that question over there. So here we have P-write data. It says 32 bits wide, right? And it goes to all of the completers. We have P-write data and P-enable. Those go to all the completers as well. P-address goes to everything, right? So this is good in the sense that a lot of parallelization, you don't want to have an address, its own dedicated address pin bus to every single one. It wouldn't make sense. The thing that it does have here is P select goes to each individual. Okay? And that is important to remember, that there could be multiple registers in here, multiple things that will, multiple locations where data can be stored. So it have multiple addresses, just like your GPIO-A port has lots of different addresses in it, some for the control, one for input, one for output, that's all being selected with one P select. Clock is going to everything. Yep, everything is clocked. The one difference or oddity that I had not appreciated when I first started learning this architecture is that every completer peripheral has its own bus back. Right? So that means that for every completer, there's another 32-bit bus that goes back to the requester, and then the requester has to take in 32 times n inputs. Now, we just talked about how, wait, you know, I thought you didn't want to have lots of pins. This is all on device, so you can have as many inputs and outputs for a device you want. I mean, routing does get hard eventually, but that's the architecture. Why would they choose to do this? What could be one reason why they would choose to have a bus for every completer to go back to the requester? Yeah.
Could be because if you combined all of them into one, you would have to deal with the problem that the completers themselves set the voltage across each wire, which can, so you need to kind of like configure each completer to like get off the wire and stuff.
Yeah. So that would be a problem. The other one is, so that's definitely, you don't want to have a bus contention where this guy's accidentally trying to set highs when that one's setting lows, and you have a short circuit. The other issue is that compared to the requester, remember the requester's going very fast, 100 megahertz or so. The completers could be dealing with these horrible things called like humans that are so slow. You push the button and it's just ages, right, just to push a button. And so if a completer's task is to interface with the outside world, it may be very, very slow compared to the core. So it needs to have wait states. It needs to wait a long time. So you don't want to have one completer blocking all other tasks that the requesters or peripherals are doing on your chip. So this one can take a long time to set up its data. When it's ready, it can instantiate P-ready. Well, I can instantiate that forward. There you go, P-ready. There's the P-ready line back to each one. So P-ready will go high when it's ready. And then the requester can scan through all the P-ready lines and said, oh, okay, you finally got back to me. Even though I had 10 other conversations with this person while you were so slow, that's fine. All right, the questions have backed up here. Did I answer your question?
Yeah, I think so.
Okay, I forgot what it was, but I knew I'd get to it.
Does that mean the requester has to have separate state machines for each completer that it wants to get data from?
What do you mean by that?
If you're in the process of talking to completer 1, let's say it's trying to get some data from the outside world, and you said like you can do 10 transactions with completer 0.
Yeah.
How does the requester still keep track of the state that like, oh, we're still waiting for completer 1 to send?
I wouldn't say each one has its own state machine, but there is a state machine that has priorities that says, okay, this pin, when this thing is ready, it has a higher priority. So maybe it'd be stacked up here, right, waiting for a bunch of lines high, and then it'll go and say, I want this one, this one, this one. So there is a priority queue. It's just buried in the RTL, the logic. We don't really deal with it because we can't manipulate it as programmers. Yeah.
In the previous diagram, you looked like kind of P enable was kind of moving at the same time as P ready. That's not guaranteed to always.
It's not guaranteed at all. That's just, we're going to go through some examples where it's not guaranteed at all.
But it is P enabled, like triggering the, P must happen before P ready can even happen.
Yeah. Yep. Okay. Yeah.
So for one of them, for P enable, like it seems like we're all waiting for all the other ones to get in place before P enable to be set to high.
Correct.
Okay, so like it has to wait for everything else before it gets set.
Correct. And I mean, that's just saying, it's like a flow control thing, because if all the bus is changing, right? Then how do you know when how does the completer know when the bus is finalized in its final state? So, I mean, so it's just about redundancy. It's not the only way you can make a bus structure, but it's a good way to make a bus structure. Yeah.
There can be like different latencies or between different completers. Is there sort of out feature of this?
Yeah, we never get into it. A lot of this is not exposed to us as programmers, but you will see understanding the bus structure and why things take weird amounts of time. That's why I want to impart with you guys. So you'll never have to really worry about the timeout features. There's other control lines about errors and timeouts that I didn't show you. All right, so let's go through a toy example. I think I got this right. I just redid it this morning. So let's say that we have APB requester and two completers, devices D1 and D2. D1 has a number of addresses it's going to respond to, right? So this peripheral will respond to 1000 to 1000F, this peripheral 1010 and 1001F, okay? And so any addresses that are outside that range, the device won't respond to, but it has multiple register banks, let's say, inside of it, which it could respond to. So it's got to respond to multiple addresses. The Cortex-M processor core is going to complete the following instructions. So it's going to say store R0 into the address represented by R1 with an offset of 4, and then you're going to be given some values for the address. So to go back to last week's lecture, this is what you would see, right? So the store function, we're going to take this address, this is the address, yes, to some location. We're going to offset by 4 because this is just offset indexing. We're not going to increment, then we're going to store the value here, which is coffee. It's going to get stored in this address. And we're not going to go in advance this value because this is just offset indexing. It's not pre-indexing or post-indexing. So this is, from the core's point of view, what's happening. And I want you guys to tell me, and I have worksheets for you. So what is the advanced peripheral bus traffic look like to cause that to occur? All right, so all that happened. Let's see, that's number 2. So what bus traffic must have occurred as a result of those instructions being issued? And remember, please, sorry, I put them right on there. Remember, you'll be turning this in at the end of class for class participation credit. So if you want to keep your copy, just take a picture of it. Yep.
Are these like based on correctness or completion?
What's that?
Is it based on correctness or completion?
This is based on completion. About effort. Try it.
Sorry. No, you're good.
All right. And then I'm sure I ran out somewhere. Great, thank you. Does anybody need one? Great. I'm not accounting. Does anybody need one? No. Okay.
Get pumped off by just like, I don't know if they want to put it Just doing a 3
How will you start this horrible problem?
So I think on the right, we'll have to go as the
And that's a good place to start now. For both of them?
yeah, just for
So I think it's actually P right. You can look back at the slides, but P right goes to every peripheral. So then this, I would put it high on both of those.
I just go because our partner just got.
You're so far ahead. You're trying to do worksheet 2.
Scatter only occurs on a rising edge.
Why do they write
The 2 different devices.
Terrified students here. What's going on? You're looking at that, yeah, perfect. Alright, so there's a diagram that has all the wires and stuff.
I think it'd be like, I think you draw it like outside.
Yeah, okay. So, where does address go? Which peripherals go to? It's labeled up there. All right, so the top diagrams for D1, the bottom diagrams for D2. These are the signals hitting the completer's interface. However, your sheets don't have D1, D2, so it's very confusing for you. So what is the address bits going to be? One question is, what's it going to be for D1? Is it going to be the same for D2? What do you think?
How long is the same difference?
I think they're the same because if I look here, the requester goes from both devices. So the same instance is going to have the same data on it. All right, so you should be drawing based on what D1 and D2 sees, the input pins on the requesters. So for instance, we know that the address line is shared. The address lines go to every peripheral, therefore the address seen by D2 is going to be the same as D1. So you get a freebie there. You can think about what are all the lines that are shared between. That's going to get you half the problem there. Yeah.
The question when you're drawing the address here, like high and low.
Yep. You just put your data right in there. Just write it.
So just assume it's in there. Okay, gotcha.
Yep.
Assume the top one is D1.
Hi. That's fine. I can help. So like this is D1, that's D2. This thing generated some P data.
Yeah, but also.
I just have that one.
I'll just copy it there.
Tell me. It can. I don't really care. I would say either starting with all these examples show you what the state was previously, so you can start drawing the same.
Quick question. Sorry, I missed the ago, but like for here, it's that high T1. Here we don't. Are we assuming that here we don't know what they are, or they're zero?
Oh, address. You know what the address is.
Just show that it changes.
Right? Yeah. For the address is R1. Address. You just write the address right in that line.
Here's like the address.
I was gonna say like
Since we
would it that'd be the same for P, right?
Actually, I think I asked my question. I don't even know the address, but for the signal for P address.
I think you want D2, right?
After you already too.
Because they said the address.
These are like kind of arbitrary.
I'm trying to trick the students. You figured out my trick? That's too easy. Okay. I like that. That's great.
Especially
Yeah,
do tell.
try to trick students and they figured it out. It makes me upset.
I went last year to like both days. Suck it out.
Where's address?
If they're like just extremely exceptional, I'm like, they're not gonna like, yeah, they're not gonna.
Yeah, so that's the data. That's right there. It's R1 plus 4.
Yeah.
Okay. The right.
Actually should be slight.
Oh, wait.
No, literally, like I'm in a group check before sending the QR code.
They have you ready. They do different tasks. Right? Here, say, is the GPL port. This one is the camera interface.
Probably one small cycle behind. No, not. I don't know about
I think it's directly connected probably.
Because like once
He's ready. For you to sample it, Mr. Requester.
You live in Washington, right?
The other ones except for
X1004.
This thing and this thing can both but only one of them goes high, right? Because each one has individual piece lines.
Okay.
Those are different.
Okay, the double lines are sure. So only the double lines.
The double lines mean it's a bus of multiple.
So the select for D1, which is being used, is high.
I think the only they don't have open house.
transmit the data.
Guys doing over here?
The only thing is different is
It's Monday. I think on Monday.
It tells you this instruction tells you what the value is. But I'm trying to trick you. Okay, so what
No, but the thing is, it's high in your It's high.
That's what you're learning here. You don't have to be good. You have to be good on the exam, not now.
I mean, it could. Okay. I'm not entirely sure the total.
It's just the exact same thing.
There is overlap today. Yeah. I looked at it wrong.
Address is going to be the same. Okay.
Yeah. They're going to be the same as the top. It's just the PSL and everything else is going to be low.
I didn't. Well, let's see. So here, so this example is. And I just put this.
I wasn't ignoring it.
It's like one cycle.
Because you burned out. Okay. Yeah, D1's being written.
I'm saying for R1, the 0x100,000.
I'm not sure if I did this right.
No, that's fine. I'm like so confused. I don't know where to start.
I think. Well, you just I was just copying from this. So this one should look exactly like that.
Right.
Yeah, I think we're right into the DY. But this one though, because it's not actually getting data, this is low. And there's no ready because it never writes. These are shared, I think. Able, write address, and write. It's right operation. Yeah. That's no idea if it's right. So that makes sense. Okay.
We have
Want me to teach you?
What's the only one that's
After on this one, it was changed and put it in my phone.
also individualized?
Oh, you did like it? Okay. Which is being written to and which is not.
I don't know. If you're not reading the bar data,
This is the same.
you said right. You're not reading.
Are you ready? Should we go through this horrible example? Please, he says stop. If I only teach you half the things, how are you supposed to know things? That's right. Okay. Let's look at this example here. So this is, you're essentially recreating this diagram from the perspective of the two completers, or D1 and D2. And instead of putting in the word address 1, you just write in the hexadecimal value here. And instead of putting in data, you can put the hexadecimal value here. But essentially, all this is true, and you might need to spend some time walking through the slides and just remembering or learning what each one of these things actually does. We'll go through it right now. But that's the kind of trick of this problem. So now we'll go through here. All right, so how do we get copy from both these signals? Let's see, what did I write? So the address, right? What's the address going to be? Well, the address was stored here in R1. Well, here's the address. But it was offset indexed. So it's not 1000 is 1004. That's what would be represented on the data bus line C by the peripherals, right? Because on the fly, this instruction is appended by 4. What do you think about that? Yeah. You gotta be loud.
Is there a reason it's only for 2 cycles?
It's the only reason it's only for 2 cycles. That's all you need, technically. There's no good reason. There's no reason you should know that the requester went and did a different task. So let's just say it could be on forever, because I didn't give you another instruction afterwards. Yeah.
Why is there a P adder change at TP?
Why is there a what?
P adder change at TP.
Oh, why is it change here and not here?
At TP.
T3? Oh, the same question he asked. Just arbitrary, the requester decided to do this, you wouldn't need to do this. Okay? If I put another instruction there, then it would start doing that next instruction. That's the next instruction. Okay, let's go forward a little bit. P right goes high, right? So you could have started drawing everything at T0, it would have been fine. The way these diagrams are typically done in the data sheet is that you start at T1, I don't know why. I'm not going to take points off if you start in the wrong spot, or not even the wrong spot, if you start T1 versus T0. If you start at T4 and run out of space, I'll be annoyed. But so here it's a right. Why is that a right? Because this is a storing data into peripheral. Here is a right. So right goes high, telling the peripheral that it should be accepting data and not pushing data back. Yeah.
Again, there's no reason why it changes that T3.
No reason. No reason. Just to cause more confusion. All right. P select. It only takes 2 cycles to complete this transaction. That's why it changes. We're just really demonstrating here, or these examples demonstrate that it could be something afterwards because it only takes 2 cycles. You didn't know that I didn't explicitly state that the peripheral only takes 1 cycle to complete after it's been set up, but it does. Yeah.
So when P select is switching at T3 to the second switch,
yeah.
Is that because you're just saying some job is happening there, or does that happen?
New task is getting done over here. Okay. Don't worry about anything after T3. Stop worrying. That's 3 questions.
The reason I asked that is in the other the diagram where it says so what's happening here.
Yeah.
All the other ones don't do that, but P select does do that. So I was wondering if there's a different reason for that.
Yeah.
Like there is no other job happening here, but this one's.
Oh, there is jobs happening here. It's just the address is the same.
Okay, I see.
Address didn't change. Maybe it's doing 2 writes to the same address. I don't know why. It might want to. All right. So we got P enable. P enable is stating that the data input onto D1 has been instantiated, right? It is available, ready to be clocked in. So this goes high, telling the peripheral it's time for you to do your thing. Yes.
Why does P write use high, low to high, but then P cell and P enable use like low to high?
Why does P select go from low to high while
P write go from high, low to high?
I don't know. This is how those architects, people smarter than me, decided to make their bus. I'm just here reporting to you how it works.
If your peripherals, sometimes, so if you're running into, you're sometimes running into a memory of short line that takes like different amount of cycles per peripheral.
Sorry, so if the peripheral takes multiple cycles.
Multiple peripherals and they vary.
Yes.
How many cycles?
Yes.
Does that affect the design of the processor?
Yes. So you will find, if you do any detailed clocking, that it's rare to get things done like in 1 clock cycle. Do a memory read, it's not 1 clock cycle. It's at least got to be 2 clock cycles. But typically it can be much more clock cycles because of wait states. Yeah.
Why does P enable not go high until the middle?
Well, first you have to instantiate all the data on the bus. So, and it has to happen 1 cycle after the data is instantiated. This example arbitrarily shows that at T1 the change occurred, and now here the bus is transitioning, the data set up, and now we're going to do it. All right, in the interest of time, we'll keep going. We got coffee here. So that's the P write data. That's the data coming from the requester to the responder. Or no, what do we call them? Yeah, I don't know, the requester and the completer. So we have coffee. How do we know it's coffee? That's a great question. So in this command, it says that we're going to store the value that's located R0 which is coffee, and we're going to place it in the address defined by R1 plus 4, so 1000 plus 4. So here you're going to see coffee on the bus. And this is just a nomenclature, right? This is just showing it's a 32-bit bus, and that's the data. I didn't want to draw 32 lines. My hand gets tired. OK. And then P-ready said, well, OK. P-enable went high, and this says, well, I'm immediately available. I will be ready. And then data's clocked in, and then it's able to transition. All right, so now we can say, what's on D2? So it's the same address. If we look back at the diagram with the two completers and all the yellow, or all the colored signals, we see that address goes to everything. We see that P-write goes to everything, so that's the same. P-select is not the same, because this address range here so D1 will respond to that address range. This is within the D1 address range, so the requester only raises the line for the peripheral that's in that address range. Now, there still could be multiple destinations within some peripheral, so that's why it's not just it's not just one P-select for everything. You have different addresses inside of that thing that will respond. And we get to P-enable. P-enable is the same for everything. It doesn't matter. It just doesn't care because it's not been selected. D2 says, well, you can P-enable all you want, but I don't really care. I'm not selected. The data going into D2 is the same as D1, still coffee. And it doesn't matter if it's P-ready or not. This bus is stable. It doesn't matter because it was never selected in the first place. So I'll take questions in a second, but the key thing to remember is there's only a few lines that are actually different between those because we want to reuse all these data lines on chip. OK. What questions do you have?
Why is the P-enable line the same? Because don't you want to enable like D1 or D2 depending on if it's like that just be like
P-enabled is more stating, maybe it's a nomenclature problem. It's more stating that the data on the bus is stable and ready.
Oh, the data on the bus. OK, gotcha.
Right? Not P-select is selecting, back to somebody's question, I want this particular device. P-enable says data is ready. Yeah.
P-write?
Yeah.
P-write is 0 for read and 1 for write. For that, ever goes down to write.
He says it starts.
If it was a load, then it would be read.
So it would only be
Right. You can't, because it's on the bus. That's going back. Hold on. We go back to this diagram. You got the core. You got the devices. Here, a store will only cause that line to be high, and a load will cause the write signal to be low. Yep. What do I have? I have 1 minute. What can I teach you in 1 minute? I must be able to teach you something.
You wrote down the value of these.
I'll teach you one more thing,
for sure, but
and that's it. All right. So let's say you wanted to control the lowest significant bit of an LED. Okay? You could have a I'll just do it next time. You guys are already out of here. Your brains are fried. We'll do it next time.
All right, it says it's not ready.
Yeah, please turn your worksheets in to get credit.